far out past the orbit of the Earth, drifting slowly at a point in space about 1 million miles from us. A telescope has spent the last few years doing something quietly extraordinary. It has been looking backward in time, catching light that left its source before the Earth existed, before the Sun existed, in some cases before almost anything existed. And what that telescope has been sending back has left a number of very careful, very cautious scientists saying things they do not usually say in public. This is a story about that telescope, the James Webb Space Telescope, and about a handful of small, stubborn discrepancies between what it has found and what nearly a century of careful cosmology predicted it would find. None of these discrepancies are, by themselves, dramatic. They are the kind of small, persistent gaps that show up in careful measurement all the time. The kind that usually get explained away within a few years by a better calibration or a more refined model. But these ones have not gone away. They have gotten sharper with better data, not softer. And there are now 4 of them, independent of each other, each pointing at roughly the same part of the theoretical structure that describes the universe. To understand why that matters, it helps to start with one particular scientist, and one particular sentence he said in public a while back. His name is John Mather. In the 1990s, Mather led a NASA mission called COBE, short for the Cosmic Background Explorer. COBE's job was to measure something called the cosmic microwave background, which is the faint leftover heat from the early universe, a kind of afterglow spread evenly across the entire sky. That afterglow comes from a moment roughly 380,000 years after the beginning of everything, when the universe had finally cooled enough for atoms to form and for light to travel freely for the first time. Before that moment, the universe was an opaque, glowing plasma. After it, light could finally move in straight lines. And some of that very first light is still reaching us today, stretched out by billions of years of cosmic expansion into faint microwave radiation. Mather's instrument measured tiny temperature differences in that afterglow, variations of about 1 part in 100,000, scattered across the sky in a very particular pattern. That pattern is not random. It is a direct fingerprint of the density fluctuations that existed in the infant universe, the seeds that would eventually grow, under gravity, into galaxies, clusters of galaxies, and the vast cosmic web we see today. When Mather's team measured that pattern, it matched, with remarkable precision, what the standard theoretical model of cosmology predicted it should look like. For that work, Mather shared the Nobel Prize in Physics in 2006, not for inventing a new idea, but for confirming an existing one so precisely that it left almost no room for doubt. In other words, Mather is not an outsider to cosmology, sniping at the field from a distance. He is one of the people who helped build its foundation and personally verified that the foundation was solid. So when a telescope came along a couple of decades later and started returning results that did not fit that foundation, and when Mather looked at that new data and said, in a public setting, for blunt words, this is not our universe, it was worth paying attention to. He did not publish those words in a peer-reviewed paper wrapped in careful statistical caveats. He said them plainly, and in the time since, no one with comparable standing in the field has stepped forward to say he was simply wrong. That kind of silence, in a field as competitive and rigorous as cosmology, is itself a small piece of evidence. Scientists correct each other constantly, often bluntly. When a claim this large goes unchallenged by the people best positioned to challenge it, it usually means the claim is at least worth taking seriously, even if nobody yet knows exactly what to do with it. So what did Webb actually find that provoked that reaction? The story starts with galaxies. Very old, very early, very distant galaxies. In February of 2023, a team led by the astronomer Ivo Lab published a paper describing 6 galaxies that Webb had photographed at an almost unbelievably early point in cosmic history, somewhere between 500 million and 700 million years after the beginning of the universe. That might sound like a long time, and in an everyday sense it is, but in cosmic terms it is ennobling. The universe itself is roughly 13,800 million years old. 500 million years after the beginning is still very close to the starting line. What made these 6 galaxies strange was not that they existed. Astronomers expected some galaxies to have formed by that point. What was strange was how much mass they already contained. Each of these objects appeared to hold a stellar mass equivalent to tens of billions of suns. Taken together, Labby's estimate suggested that these 6 galaxies alone held more total stellar mass than the standard model of cosmology said the entire observable universe should have been able to produce. By that point in its history, an astrophysicist named Mike Boylan at the University of Texas at Austin read the paper and gave the galaxies a nickname that stuck: universe breakers. His reasoning was straightforward. For a galaxy to build up stellar mass, gas has to collapse under gravity and ignite into stars. Gravity is not an adjustable process. It moves at a rate fixed by physics, and that rate sets a hard ceiling on how quickly matter can collapse and how quickly stars can form, live, and produce successive generations of new stars. There is no known mechanism that lets matter collapse faster than gravity allows. And yet these galaxies appeared to have assembled more stellar mass in less available time than that ceiling should have permitted. The natural first response from the scientific community was not excitement. It was suspicion, and that suspicion was entirely appropriate. The history of astronomy includes plenty of cases where an instrument produced something that looked revolutionary and turned out, on closer inspection, to be a calibration problem. In 2011, a loose fiber optic cable briefly made it look like scientists had detected particles traveling faster than the speed of light. They had not. It was a wiring fault. In 2014, a signal that looked like it might be direct evidence of gravitational waves from the very early universe turned out to be dust in our own galaxy that had not been properly subtracted from the data. Both of those false alarms were caught quickly, because the scientific process for hunting down systematic errors is thorough and well practiced. So astronomers applied that same process to Webb's early galaxy results. They checked the distances and ages of these galaxies using 2 independent techniques. The first, called photometric redshift, estimates a galaxy's distance and age by studying the overall color of its light, which shifts in predictable ways as the universe expands. It is a powerful method, but it relies on assumptions about what kind of galaxy is producing the light. The second technique, spectroscopic confirmation, is more direct. It measures the precise wavelengths of light coming from specific chemical elements within the galaxy, wavelengths that shift by an exact, calculable amount depending on how far the light has traveled and how much the universe has expanded since it was emitted. This second method does not depend on assumptions about galaxy type. It is about as close to a direct measurement as this kind of astronomy gets. Through the course of 2023, spectroscopic campaigns targeted the most extreme of these early galaxy candidates and applied this harder, more direct test. The results did not shrink the sample or explain it away. They confirmed it. the galaxies really were where Webb said they were, and they really did contain roughly the mass that the earlier estimates suggested. At that point, the conversation among astronomers shifted. The question was no longer whether the instrument had made an error. It became a question about what it means that the universe apparently contains objects that its own well-tested history says should not be possible yet. And the story did not stop with mass. Webb's spectroscopic data revealed something else layered on top of the mass problem. Something, in some ways, even harder to explain away. Light carries information about the chemical makeup of whatever produced it, encoded in very specific wavelengths, sometimes called spectral lines, that correspond to particular elements. When astronomers studied the spectra of some of these very early galaxies, they found signs of carbon, oxygen, and iron. None of those are primordial elements. The universe, in its first few minutes, produced almost nothing but hydrogen, helium, and a trace amount of lithium. Every heavier element, everything from carbon up through iron and beyond, had to be manufactured inside the cores of stars through a slow nuclear process, and then scattered into surrounding space when those stars eventually died, often in supernova explosions. That scattered material then had to collapse again to form a new generation of stars, which would be chemically richer than the first, having inherited the debris of their predecessors. This process is called nucleosynthesis, and like gravitational collapse, it has a pace fixed by physics. You cannot inherit chemical richness from stellar generations that have not yet had time to live and die. For these very early galaxies to show the chemical fingerprints they showed, the universe needed to have already completed multiple full cycles of star formation, stellar death, and chemical enrichment, all inside a window of cosmic time that the standard timeline barely had room for a single cycle, let alone several zones. Now there were two independent lines of evidence: mass and chemical complexity, measured with different instruments using different techniques, both pointing at the same underlying problem: not enough time. If the standard timeline for how the early universe assembled its structure is wrong, it is worth asking whether it was already showing signs of being wrong before Webb ever looked, and it turns out there were other cracks found years earlier that had never quite been resolved. One of those cracks concerns something called the Hubble constant, a number that describes how quickly space itself is expanding, or more precisely, how quickly the distance between any 2 points in the universe grows over time. Pinning this number down precisely has, for most of the modern history of cosmology, been considered one of the field's central practical challenges. Not because the idea was unclear, but because measuring it accurately enough to matter required instruments that, for a long time, simply did not exist. Two different methods for measuring the Hubble constant were refined in parallel over the past few decades. One method uses the cosmic microwave background itself, the same afterglow Mather's instrument measured, and works backward from its detailed pattern to infer how fast the universe must be expanding today. Using this method, the European Planck satellite arrived at a value of about 67.4 kilometers per second per meter. The other method builds what is called a distance ladder, using certain kinds of stars called Cepheid variables, along with a particular type of exploding star called a Type 1a supernova, both of which can be used as reliable distance markers because their intrinsic brightness is well understood. This method arrived at a noticeably higher value, around 73 kilometers per second per megapasec. Both measurements are internally consistent. Both have been independently verified many times over. Both rely on well-established underlying physics, and yet they produce numbers that cannot both be correct if that underlying physics forms one single coherent picture. Because the gap between them, about 9%, is far larger than the margin of error either method should have. In 2019, the astronomer Adam Rees, who had shared the Nobel Prize in Physics in 2011 for the earlier discovery that the universe's expansion is accelerating, pointed out that this disagreement, often called the Hubble tension, had crossed what physicists call 5 standard deviations, sometimes called 5 sigma. In particle physics, 5 sigma is generally treated as the threshold for declaring that something real has been found, rather than a statistical fluke. Rees was not announcing a new discovery in the usual sense. He was announcing that the disagreement between these two ways of measuring the same fundamental number had become too large to attribute to chance. He used a blunt phrase to describe it: something is fundamentally wrong. That statement came before Webb launched, before the universe-breaker galaxies were reported, and before another major survey added its own piece to the puzzle. Over the following years, the field tried, systematically and in good faith, to make the Hubble tension go away. Teams rebuilt the Cepheid distance ladder from scratch, using different reference stars, different calibration methods, different analysis software. The gap survived. Other teams reanalyzed the Planck cosmic microwave background data using modified assumptions about the conditions of the very early universe. Some of these efforts shifted the derived numbers slightly, but none of them closed the gap without creating new inconsistencies somewhere else. Theorists proposed the existence of something called early dark energy, a brief burst of additional energy in the first 100,000 years of cosmic history that could nudge the early universe measurement closer to the late universe measurement. These models helped a little at the margins, but they did not close the gap. They mostly just moved it around then. Starting in 2023, the team responsible for the Cepheid distance ladder switched from using the older Hubble Space Telescope to using Webb itself for their key calibration measurements. Webb is sharper and more precise, so the new measurements came out cleaner than before. And the gap held, sitting at essentially the same value it had held for years of increasingly careful refinement. A discrepancy that survives every systematic check, that grows statistically sharper as the instruments improve, and that resists every proposed internal fix, stops looking like a measurement problem. It starts looking like a physics problem. Something appears to be happening in the space between the early universe and the late universe, in the region where the standard cosmological model is supposed to connect the two smoothly, and apparently does not. Now consider a third, independent line of evidence. This one coming from a project called the Dark Energy Spectroscopic Instrument, usually shortened to DESI, over about 5 years. DESI mapped the three-dimensional positions of roughly 6 million galaxies across a huge span of cosmic history. That is not a small sample. It is closer to a census. DESI was specifically looking for something called baryon acoustic oscillations, which are essentially fossilized sound waves, ripples that moved through the hot plasma of the very early universe and left behind a characteristic scale in how matter is distributed. That scale can be used like a cosmic ruler, by measuring it at different distances, which correspond to different points in cosmic history. Scientists can reconstruct how the rate of the universe's expansion has changed over time, almost like assembling a frame-by-frame record of cosmic growth. What DESI's frame-by-frame record showed was surprising. a quantity called the cosmological constant, often written as lambda, which represents the energy density of empty space and is the driving force behind the accelerating expansion of the universe, did not behave the way a constant is supposed to behave. Its effective value appeared to shift across cosmic time, stronger at some periods, weaker at others. Data published across multiple papers in 2024 from an international collaboration involving hundreds of physicists showed a statistical preference for what is called dynamical dark energy, meaning a vacuum energy that evolves over time, rather than sitting fixed throughout the universe's entire history. This matters enormously, because the cosmological constant is not some minor detail. It controls the rate at which the universe expands, and its long-term behavior over trillions of years determines how everything eventually ends. The standard picture, built on the assumption of a fixed, unchanging lambda, predicted one specific ending: the universe expands forever at an ever-increasing rate. Galaxies drift apart until light from one can no longer reach another. Stars burn out one by one, and eventually, over almost incomprehensible timescales, even black holes evaporate, leaving behind a cold, thermodynamically exhausted emptiness, sometimes called heat death. That picture required lambda to remain at its current value indefinitely into the future. If lambda is not remaining constant, the possible endings multiply. If dark energy grows stronger over time, the universe could eventually be torn apart in what is sometimes called the Big Rip, a scenario in which the accelerating expansion eventually overwhelms every other force in sequence, first pulling apart galaxy clusters, then individual galaxies, then solar systems, then planets, and finally atoms themselves. If dark energy instead weakens over time and eventually reverses, the expansion could slow down and turn back into contraction, ending in what is called the Big Crunch, a universe that collapses back toward the kind of dense state it began in. And if dark energy oscillates, the long-term trajectory becomes something that no current model can reliably predict at all. 3 very different possible endings, each corresponding to a different behavior of one single variable that, until recently, everyone assumed was simply constant. To understand how deeply this cuts into the foundations of modern cosmology, it helps to look at what the standard model, usually called lambda, cold dark matter, or Lambda-CDM for short, actually claims the universe is made of. In this model, about 5% of the universe's total energy content is ordinary matter, the kind that makes up stars, planets, and everything we can directly detect. About 27% is dark matter, an invisible form of mass that does not interact with light but does interact gravitationally, providing the scaffolding that lets visible structure form in the first place. And about 68% is dark energy, the mysterious pressure driving the accelerating expansion. Lambda-CDM is, in a real sense, the operating system of modern cosmology, the framework inside which nearly every simulation, every prediction, and every statement about the universe's past and future gets computed. For roughly 3 decades, this model performed so consistently across so many different kinds of observations that the underlying question of whether it was truly describing reality, or simply approximating it very well within a limited range, stopped feeling urgent. The pattern of the cosmic microwave background matched it. The statistics of how galaxies clustered together matched it. The baryon acoustic oscillation scale matched it. The relative abundance of light elements produced in the earliest minutes of the universe matched it. Each successful confirmation reinforced the next, until the distinction between the model and reality itself began to blur in the minds of many working scientists. And then Webb made a request the model was not built to handle: early galaxies with the wrong mass, Lambda-CDM strains to explain it, chemical complexity appearing at the wrong point in cosmic time, Lambda-CDM strains to explain that too, an expansion rate disagreement between the early and late universe that refuses to close, Lambda-CDM strains there as well. Any one of these failures, taken alone, might reasonably be written off as a calibration issue or a gap in the modeling. Taken together, they start to look like something more specific, because they are not occurring at the fuzzy edges of the model's predictions, where a little uncertainty is expected and tolerated. They are occurring right at the predictions the model was most confident about. That is not the pattern measurement errors usually follow. There is a fourth anomaly, one that tends to receive less public discussion, possibly because taking it seriously leads somewhere structurally uncomfortable. It concerns something called the Hercules Corona Borealis Great Wall, an enormous filament of galaxies stretching across roughly 10 billion light-years of space. That is about 10 times larger than the scale at which the universe is supposed to look smooth and uniform, according to a foundational assumption baked into modern cosmology called the cosmological principle. The cosmological principle holds that, at sufficiently large scales, the universe looks roughly the same everywhere, smooth and uniform, without any particular direction or location being special. This assumption is built directly into the mathematics of Einstein's field equations before a single observation is ever taken into account, and every version of Lambda-CDM depends on it being true. The Great Wall exceeds the scale at which that smoothness is supposed to be guaranteed by roughly a factor of 10. If the cosmological principle turns out to be wrong, then Lambda-CDM is resting on a foundation that was never quite solid. If the cosmological principle is correct, despite the Great Wall's existence, then the Great Wall requires an explanation involving physics that is not present in any model currently on the table. Either way, it is a loose thread. It is worth pausing here to consider what dark energy actually is, or perhaps more accurately, what it is not. The cosmological constant first appeared in Einstein's equations back in 1917, added by hand to prevent his model of the universe from collapsing under its own gravity. When Edwin Hubble later showed that the universe is expanding, Einstein removed the term, reportedly considering it one of his greatest mistakes. Then, in 1998, observations of distant supernova, led independently by teams headed by Saul Perlmutter, Brian Schmidt, and Adam Rees, showed that the universe's expansion is not slowing down under gravity, as everyone expected, but speeding up. The cosmological constant was reintroduced, this time reinterpreted as the energy density of empty space itself, sometimes called vacuum energy. The irreducible energy that even a perfectly empty region of space is thought to carry. Quantum field theory predicts that empty space should have a non-zero energy density, arising from the constant appearance and disappearance of what are sometimes called virtual particles, which briefly borrow energy from the vacuum before vanishing again. When physicists calculated what this vacuum energy should theoretically be, and compared it to the actual observed value of the cosmological constant, they found an almost unbelievable mismatch. Somewhere between 40 and 120 orders of magnitude too large. That is not a rounding error. It is by a wide margin the largest discrepancy between a theoretical prediction and an observed measurement in the history of physics. Physicists have taken to calling this the vacuum catastrophe, and the name fits. There is currently no accepted solution. Dark energy, as represented by lambda, works remarkably well in matching what we observe, while the theory that is supposed to explain where it comes from is wrong by a margin that dwarfs every other failed prediction in science combined. And now the DESI results suggest that even lambda's observed behavior is not quite what everyone assumed. Dark energy is not so much an explanation of what drives the universe's expansion as it is a very successful placeholder standing in for something nobody yet understands. This theme of things fitting suspiciously well, without anyone fully understanding why, shows up elsewhere in physics too, in a way that is worth sitting with for a while, because it eventually connects back to the same underlying question. In the early 1950s, a physicist named Fred Hoyle was trying to understand how heavy elements form inside stars. Carbon turns out to be a critical bottleneck in this process. Without a reasonably efficient way to produce carbon, the chain of nuclear reactions that eventually builds oxygen, nitrogen, iron, and everything else on the periodic table simply cannot get going. Carbon forms when 3 helium nuclei collide and fuse together in a 2-step sequence, but under ordinary stellar conditions. The odds of this happening are astronomically low, far too low, in fact, to account for the amount of carbon that actually exists throughout the universe, including inside every living thing that has ever lived. Hoyle reasoned backward from that fact. Carbon clearly exists in abundance, he thought, so the reaction rate producing it must be far higher than raw probability alone would suggest. That could only happen, he argued, if there were a specific nuclear energy state inside the carbon. 12 nucleus that dramatically boosted the reaction rate by resonating with the energy of the incoming helium nuclei. This was not something he calculated from first principles using quantum mechanics. He inferred it purely from the observation that we exist, and therefore the universe must permit the specific chemistry that produced us. He told experimental physicists at Caltech exactly what energy level to look for. They looked. It was there, not approximately, but very close to the exact value Hoyle had predicted. A value derived from no prior calculation and no prior measurement, only from the premise that observers exist to ask the question in the first place. This points towards something larger. The carbon resonance is just one example among a set of roughly 26 fundamental physical constants that together determine how reality behaves. These include things like the strength of gravity, the speed of light, the mass of the electron, the strength of the electromagnetic force, and the value of the cosmological constant itself. Change almost any one of these numbers even slightly, and the universe loses its ability to produce complexity of any kind. Not just a little less complexity, but essentially none at all. Reduce the strength of the force that binds atomic nuclei together by around 2% in either direction, and protons can no longer bind into larger nuclei. Chemistry stops at hydrogen. No stars capable of producing heavier elements, no supernova, no carbon, no planets, nothing capable of thought. Increase the cosmological constant by a factor of even a few hundred above its actual observed value, and the universe would expand so quickly after its earliest moments that matter would never gravitationally clump into galaxies or stars at all. Shift the ratio between the strength of electromagnetism and gravity by roughly 1 part in 10 to the 40th power. An almost incomprehensibly precise adjustment, and stars either burn through their fuel far too quickly to allow life to develop nearby, or never ignite in the first place. 26 numbers, each sitting at a value that happens to permit complexity, each apparently unrelated to the others as far as known physics can tell, and together forming an arrangement that allows stars to burn steadily for billions of years, allows heavy elements to form and scatter and recombine into chemistry, and allows that chemistry to eventually build structures capable of wondering why the numbers are what they are. 3 broad explanations have been proposed for this apparent fine-tuning, and each one, followed honestly to its conclusion, asks you to give up something you might not expect. The first is called the anthropic principle, formalized by the physicist Brandon Carter in 1974. It states, simply, that we observe a universe capable of supporting life because only universes capable of supporting life contain observers able to notice and ask the question, if the constants were different, nobody would be here to wonder about it. This reasoning is logically airtight, but as an explanation, it feels almost empty. A bit like saying you survived a serious accident because people who did not survive are not available to be interviewed about it afterward. It is true, but it does not actually explain why you, specifically, survived. The physicist Lee Smolin pushed the idea further in 1992, proposing that universes might, in a sense, reproduce through the formation of black holes, and that something like natural selection could favor universes whose physical constants happen to be especially good at producing black holes, with life-friendly conditions arising as a kind of side effect. This remains the only version of the fine-tuning explanation that makes a genuinely testable prediction, though whether that prediction actually holds up remains a matter of ongoing debate within the field. The second broad explanation requires accepting that our universe might be just one among an enormous, possibly infinite, collection of universes, each with its own distinct set of physical constants, all arising from the same underlying process that produced ours. In a large enough collection, every possible combination of constants eventually gets tried somewhere, and we simply find ourselves living in one of the combinations that happened to work. This idea is scientifically motivated and mathematically grounded in mechanisms that were originally proposed to solve completely different problems, which is worth returning to shortly. It is also, in a strict sense, unverifiable, because if other universes exist, they lie permanently outside anything we could ever observe. String theory intersects with this picture in a very specific way. String theory was originally proposed as an attempt to unify quantum mechanics and general relativity, the two most successful theories in physics, each extraordinarily well tested within its own domain, and each mathematically incompatible with the other. The framework requires the existence of extraspatial dimensions beyond the 3 we experience directly, dimensions that would be curled up at scales far too small for any current instrument to probe. The specific geometry of those extra, hidden dimensions determines the physical constants of whatever universe results from it. Different geometries produce different constants, and the number of mathematically possible geometries consistent with string theory turns out to be an almost unimaginably large figure, roughly 10 to the power of 500. That is not a rough estimate or a placeholder for a large number. It is the actual result of counting distinct configurations. The physicist Leonard Susskind called this vast collection of possibilities the landscape. Our universe occupies exactly one point within it. String theory, in its current form, does not tell us which point that is, or why. A theory that set out to be a theory of everything ended up producing an enormous catalogue instead, with our particular universe sitting somewhere inside it, unidentified. The third explanation is more conservative. It holds that the constants are not truly fundamental at all, and that some deeper, not yet discovered theory will eventually show that their specific values follow necessarily from more basic mathematical principles. The same way the ordinary rules of arithmetic follow inevitably from a small set of underlying axioms rather than being arbitrary choices. This is the option with the least current evidence pointing toward it, though it remains, at least in principle, possible. What is genuinely interesting is that nobody originally went looking for a multiverse out of philosophical preference. The idea arrived almost by accident, as a side effect of solving two very specific technical problems that had nothing directly to do with fine-tuning at all. Those two problems were called the smoothness problem and the flatness problem. The smoothness problem is this: regions of the observable universe on opposite sides of the sky appear to be at almost exactly the same temperature, to a precision of about 1 part in 100,000, even though, according to the standard expansion history, those regions were never close enough together and never had enough time to exchange energy or information and settle into thermal equilibrium with each other. The flatness problem is related. The overall geometry of the universe is spatially flat to an extraordinary degree of precision, and maintaining that flatness from the earliest moments onward would have required the initial energy density of the universe to be fine-tuned to roughly 1 part in 10 to the 60th power, an almost absurdly delicate balance if left unexplained. In 1981, the physicist Alan Guth proposed a solution called inflation, in an incomprehensibly brief fraction of a second after the beginning. Guth suggested the universe underwent an enormous exponential burst of expansion, stretching regions that had once been in close contact out across the observable sky before the ordinary. Slower expansion took over, and freezing the overall geometry flat in the process. The idea worked. It made specific predictions about the pattern of the cosmic microwave background, and those predictions were later confirmed by instruments including Mather's, COBE, and its successors. For a while, nobody paid much attention to a follow-up question: what does inflation do if it does not stop everywhere? In the universe, at exactly the same moment, the physicist Andre Linde asked that question directly. In 1983, he showed that in most versions of inflationary theory, inflation does not actually stop everywhere at once. Instead, it stops locally, in scattered patches, while continuing indefinitely in the surrounding regions. Each of those surrounding regions eventually generates its own scattered stopping patches, each with slightly different physical properties, set by random quantum fluctuations at the exact moment inflation happened to end there. This process, once it gets going, has no natural global endpoint. It is self-sustaining and, in a real mathematical sense, eternal, continually producing an unlimited number of separate post-inflationary regions, each effectively its own universe, each with its own values for those 26 fundamental constants. In other words, nobody deliberately chose to introduce a multiverse into cosmology. It arrived as an unavoidable mathematical consequence of the very mechanism that was adopted specifically to explain why the sky looks so smooth and uniform. If these separate bubble universes are real, there is at least a chance that some of them, early on, collided with one another. When two expanding bubbles intersect inside the larger inflating background, the collision would deposit energy along their shared boundary and leave behind a distinctive mark, a roughly circular feature in the cosmic microwave background with a specific temperature profile. This is, at least in principle, a testable prediction. And there is a genuine feature in the cosmic microwave background, located in the direction of the constellation Eridanus, and often called the cold spot, that fits the general description. It is a region noticeably colder than the surrounding average, large enough and statistically unusual enough that standard inflationary models produce something like it by pure chance in only about 2% of simulated skies. 2% alone is not damning. It happens. But 2% sitting alongside a whole cluster of other anomalies, each independently landing at the edge of statistical expectation, starts to accumulate a certain weight. Some research groups have pointed out that the cold spot's temperature profile, a central cold region surrounded by a ring of slightly warmer material, is broadly consistent with what a bubble collision signature might look like. Other explanations exist too, including the possibility of a large foreground void or simple statistical fluctuation, and the debate remains unsettled. What is not in dispute is that the feature is real, that it is statistically unusual, and that one of its scientifically valid interpretations is that we may be looking at the faint mark left behind by contact with another universe. Sometime in the earliest instant of cosmic history, there is another thread of theoretical physics that connects to all of this, one that reaches even deeper into the question of what space itself actually is. In 1997, the physicist Juan Maldacena showed that a particular theory of gravity, formulated in a specific kind of curved spacetime, is mathematically identical, not merely similar or analogous, but truly identical, to a completely different quantum theory that lives only on the flat boundary surrounding that curved space. This equivalence, often called the ADS-CFT correspondence, has since been checked and verified across thousands of scientific papers over nearly 3 decades. Taken seriously, what it implies is that gravity itself may not be fundamental. Space-time, the curved fabric that holds galaxies together, bends light, and defines the very notion of distance, may not be a stage on which physics happens. It may instead be something that emerges from physics happening elsewhere. The way temperature emerges from the collective motion of countless individual particles, without existing at all as a property of any single particle by itself. Space, in this view, is not a container. It is a consequence. In 2010, the physicist Mark van Romstank described a thought experiment that made this idea startlingly concrete. Imagine 2 separate quantum systems, and imagine making them maximally entangled with each other, meaning their properties become deeply correlated in a way unique to quantum mechanics. Within the ADS-CFT framework, this maximal entanglement corresponds to a connected, unified region of spacetime, essentially a geometric bridge linking the 2 systems. Now imagine gradually reducing that entanglement. The geometric bridge grows longer and thinner. Reduce the entanglement all the way to 0, and the bridge closes entirely. The 2 regions are no longer geometrically connected in any sense. Crucially, the space between them does not simply become empty. There stops being any space between them at all. Remove the underlying quantum entanglement, and you do not end up with distant space. You end up with no space. This suggests that the very space we occupy is not a fundamental backdrop to reality, but rather a consequence of underlying quantum correlations, correlations that, if removed, would cause that space to stop existing entirely. This connects directly to a puzzle that occupied the physicist Stephen Hawking for roughly 3 decades. In 1974, Hawking showed that black holes are not perfectly black after all. Through a subtle quantum effect near their boundary, called the event horizon, black holes slowly emit a faint stream of thermal radiation, gradually losing mass and energy over time, until, given enough time, they evaporate completely. The trouble is that this thermal radiation, by its very nature, is essentially random, and carries no detailed information about whatever originally fell into the black hole. If everything that falls in eventually leaves only as featureless thermal radiation, then the specific information describing what fell in appears to be genuinely destroyed, not merely hidden away somewhere. This directly violates a deep principle in quantum mechanics called unitarity, which holds that information should always, in principle, be conserved and recoverable. This argument, known as the black hole information paradox, ran unresolved for roughly 30 years. Its eventual resolution came through the holographic principle, the same broad idea underlying AD-CFT. The idea is that information about whatever falls into a black hole is actually stored on the boundary of the black hole, its event horizon, rather than genuinely lost inside its interior. When matter crosses that boundary, the information describing it becomes encoded on the surface, not destroyed, and can, at least in principle, eventually be recovered from the details of the outgoing radiation. In 2004, at a conference in Dublin, Hawking publicly conceded the point. The universe, it turns out, does not destroy information. The past remains, in a precise technical sense, permanent, even if it is not currently accessible or readable in any practical way. The universe behaves like a system with a perfect memory. We simply do not yet know how to properly ask it what it remembers. There is a deeper layer to this story that grew directly out of the black hole information paradox. In 2012, a group of physicists, including Ahmed, Donald Marolf, Joseph Polchinski, and James Sully, pointed out a sharper version of the same tension, one that came to be known as the firewall paradox. According to general relativity, an observer falling into a large black hole should notice nothing unusual as they cross the event horizon, experiencing smooth, ordinary space-time the whole way through. But if information really is preserved and carried away by the outgoing radiation, then that radiation needs to be entangled with radiation emitted earlier, and quantum mechanics does not allow a given system to be maximally entangled with two completely different things at once. Followed carefully, this logic suggests that an infalling observer should instead encounter an intense wall of high-energy radiation right at the horizon, rather than smooth, unremarkable space-time. Something, the argument goes, has to give. Either the preservation of information or the smoothness of space-time predicted by general relativity, or some other assumption long taken for granted in low-energy physics near black holes. All three cannot simultaneously hold. The resolution likely requires understanding space-time itself in a genuinely new way. And this is where several of these threads, holography, entanglement, and black hole physics, start to weave back together. In 2013, Maldacena and Susskind proposed an idea usually shortened to E equals EPR. The name combines two things that, on the surface, look completely unrelated: Einstein-Rosen bridges, which are theoretical geometric shortcuts through space-time, sometimes casually called wormholes, and the Einstein-Podolsky-Rosen thought experiment, which describes quantum entanglement between distant particles. The proposal is that these two things are, at a deeper level, the same phenomenon described in two different languages, whenever two quantum systems are maximally entangled. The proposal suggests they are connected by a non-traversable version of one of these geometric bridges. Entanglement, in other words, may simply be geometry viewed from a different angle. If this is correct, the intricate web of quantum entanglement running through the vacuum of empty space may be what determines the geometry of space-time itself. At every scale, all the way up to the large, smooth structure we ordinarily perceive. This has real implications for how physicists think about the Big Bang itself. In the standard version of Lambda-CDM, the Big Bang is treated as a genuine singularity, a point where general relativity simply breaks down and all known physics reaches its limit, with no meaningful way to ask what, if anything, came before it. If space-time really does emerge from an underlying structure of quantum entanglement, then the Big Bang can instead be reframed as a moment when that entanglement structure was radically different from what it is today, rather than as a true boundary to time itself. Some approaches, such as loop quantum cosmology, replace the classical singularity with what is called a quantum bounce, a transition where the extreme conditions of the very early universe are governed by quantum effects that prevent an actual point of infinite density from ever forming. In this picture, there may have been a previous contracting phase before the bounce, with its own separate cosmological history. Other approaches, arising from certain string theory models, describe the Big Bang as the moment when two higher dimensional structures, sometimes called branes, collided, with the history before that collision extending indefinitely into the past. Webb cannot settle which, if any, of these pictures is correct, but the anomalies it has found in the very early universe are beginning to place real constraints on the range of possibilities in a way that simply was not achievable before. The chemical makeup of these early galaxies constrains how quickly the first generations of stars must have lived and died. The mass and distribution of these early galaxies constrain how efficiently structure could have formed in the available time. As these constraints continue to accumulate, they should eventually help distinguish between competing theoretical models that currently make very similar predictions about the late universe but differ sharply in what they predict about the earliest moments. It helps, at this point, to widen the lens and look at how physics has handled situations like this before, because there is a recognizable pattern buried in the history of science, one that has repeated itself more than once for roughly 50 years. One very small number sat unresolved in the scientific literature: the orbit of the planet Mercury. Mercury's elliptical path around the Sun slowly rotates with each full orbit, a phenomenon called perihelion precession. Newtonian mechanics predicted a certain amount of this rotation, caused by the gravitational tug of the other planets. But once astronomers carefully subtracted out all of those known contributions, a small residual remained, about 43 arc-seconds of extra rotation per century, an amount too small to detect without instruments built specifically for the purpose. For half a century, this leftover number had no proper theoretical home. Various explanations were proposed and tested. Some astronomers suggested there might be an undiscovered planet, sometimes called Vulcan, orbiting closer to the Sun than Mercury, whose gravity would account for the discrepancy. Careful searches turned up nothing. Others suggested the Sun itself might be slightly flattened in shape. Measurements showed the Sun was round enough that this explanation did not work either. Every attempt to explain the number within the existing framework of Newtonian mechanics produced at least one new problem of its own. The number simply sat there unexplained for decades. In 1915, Albert Einstein completed his theory of general relativity. One of the very first things he calculated with it was Mercury's perihelion precession. The result came out to 43 arc-seconds per century, exactly, without any adjustable parameters and without any special pleading. The number that had been theoretically homeless for 50 years fell directly and naturally out of a theory, built on completely different conceptual foundations. It was not a small correction bolted onto Newtonian gravity. It was a full reconceptualization of what gravity fundamentally is. The price of explaining those 43 arc-seconds turned out to be the replacement of Newtonian mechanics itself, at least as a description of gravity at its most fundamental level. The current Hubble tension sits at around 9%, roughly 2 orders of magnitude larger, proportionally, than Mercury's 43 arc-second gap ever was. And unlike Mercury's single unexplained number, there are now at least 4 separate anomalies: the early galaxy problem, the Hubble tension, the DESI dark energy result, and the Great Wall, all sitting in the position that Mercury's precession occupied back in the 1870s, theoretically homeless, waiting for a framework that can account for them. There is another historical parallel worth sitting with, this one from the very end of the 19th century. Around that same period, Newtonian mechanics faced a second small anomaly, alongside Mercury's precession, involving something called the luminiferous ether. Physicists at the time assumed that light, like sound, needed some kind of medium to travel through, and they called this hypothetical medium the ether. An experiment carried out by Albert Michelson and Edward Morley was designed to detect the Earth's motion through this ether. By comparing the speed of light measured in different directions, the experiment consistently found no difference at all, no matter how carefully it was repeated. Both this null result and Mercury's precession were individually small. Both resisted every explanation proposed within the existing framework, and both eventually turned out to require not a minor patch to Newtonian mechanics, but a genuine replacement of it. General relativity resolved Mercury's precession. Special relativity, developed by Einstein in 1905, resolved the ether problem by showing that light does not need a medium at all, and that the speed of light is the same for every observer, regardless of their own motion. Neither resolution was a modification of Newton's ideas. Both were fundamental reconstructions of what space, time, and motion actually are. A closely related pattern shows up again in the early development of quantum mechanics. Around the turn of the 20th century, classical physics ran into a cluster of small, seemingly unrelated puzzles. There was the so-called ultraviolet catastrophe, a failure of classical physics to correctly predict the spectrum of light emitted by hot glowing objects. There was the photoelectric effect, in which light striking a metal surface knocked electrons loose in a way that did not match classical predictions about how light should behave. There was the basic stability of atoms themselves. Since classical electromagnetism predicted that an electron orbiting a nucleus should rapidly radiate away its energy and spiral inward, causing the atom to collapse in a fraction of a second, which plainly does not happen. And there were the sharp, discrete spectral lines produced by hydrogen and other elements, patterns that classical physics could not adequately explain individually. Each of these puzzles was strange but survivable. Together, they formed a pattern that classical physics simply could not accommodate. The eventual resolution did not come from patching classical mechanics with small corrections. It came from recognizing that the underlying description of physical reality at very small scales was fundamentally different from the everyday classical picture. Energy, it turned out, comes in discrete packets rather than smooth, continuous amounts. The act of measurement genuinely disturbs the systems being measured. Particles carry wave-like properties, and waves carry particle-like properties. The resulting framework, quantum mechanics, did not throw away classical mechanics entirely. It incorporated classical mechanics as a limiting case, the version of physics that emerges naturally at the everyday scales where quantum effects become negligible. Classical mechanics was never wrong, exactly. It was incomplete, an approximate description that works very well at the scales where it was originally developed and tested, but breaks down outside that range. Lambda-CDM will very likely end up occupying a similar position, relative to whatever eventually replaces or extends it. It will probably be remembered as an accurate description of the Q-universe within the scales and time periods where it was actually developed and tested, while whatever comes next incorporates it as a special limiting case, extending the description into the regimes. The very early universe, the largest cosmic scales, where Lambda-CDM currently strains and fails. What might that successor look like? Broadly speaking, there are three general directions currently being explored, and none of them has yet won out over the others. The first modifies gravity itself, approaches like modified Newtonian dynamics, and various relativistic versions built on top of it, attempt to reproduce Lambda-CDM's many observational successes without needing to invoke dark matter as an invisible substance at all. These approaches have some real successes, but they struggle badly with certain observations, particularly of colliding galaxy clusters, where the overall mass distribution clearly separates from the visible matter in ways that modified gravity theories have not been able to cleanly reproduce. The second direction keeps the general Lambda-CDM framework intact, but adds new ingredients to it. Early dark energy is one example, nudging the early universe's derived expansion rate slightly and reducing the Hubble tension somewhat at the margins. The general pattern with this approach is that every added ingredient tends to solve one specific problem while creating new pressure or tension somewhere else in the model. The third direction is the most radical. It replaces the underlying mathematical substrate entirely. Loop quantum cosmology replaces the classical Big Bang singularity with the quantum bounce described earlier. Causal set theory replaces the smooth, continuous space-time of general relativity with a fundamentally discrete structure at the smallest possible scales, sometimes called the Planck scale. These are not small adjustments to the standard model. They are attempts to replace the very space-time manifold on which the standard model is written. None of these three broad directions is yet complete enough to make the full range of precise cosmological predictions that Lambda-CDM currently achieves. Each looks promising in certain respects and then runs into difficulty once it meets the complete body of available data. Whatever eventually succeeds Lambda-CDM is probably not going to be a simple extension of any single one of these three directions on its own. It is more likely to come from somewhere genuinely outside the boundaries of the current framework altogether. There is another question that Webb's observations have quietly sharpened, one that has nothing directly to do with dark energy or early galaxies, but everything to do with what kind of universe we appear to be living in. It is a question the physicist Enrico Fermi is said to have raised over lunch at Los Alamos back in the summer of 1950. Given how old and how large our galaxy is, he reasoned, if intelligent life arises with any meaningful probability at all, it should, by now, be visible somewhere, and yet the sky is silent. In 1961, the astronomer Frank Drake formalized this line of reasoning into an equation, multiplying together a series of factors: the rate at which stars form, the fraction of those stars with planets, the fraction of those planets with conditions suitable for life, the probability that life actually arises where conditions allow it, the probability that life develops intelligence, the probability that intelligence develops detectable technology, and the average length of time a civilization continues broadcasting signals that could be detected. Multiply all of those factors together, and you get an estimate for how many detectable civilizations might currently exist in the galaxy. Webb is now directly measuring some of these factors for the first time. Earlier data from the Kepler mission already suggested that planetary systems are extremely common, with most Sun-like stars hosting planets, and roughly 1 in 5 hosting something within the habitable zone. The range of distances where liquid water could plausibly exist on a planet's surface. Webb has gone further, detecting water vapor, carbon dioxide, and sulfur dioxide in the atmospheres of certain exoplanets, direct chemical evidence about worlds orbiting other stars. Every factor in the Drake equation that Webb is actually able to measure has been trending toward a larger, more optimistic answer. And every factor Webb cannot measure whether life genuinely tends to arise where conditions allow it. Whether intelligence, once it appears, tends to survive long enough to become detectable, carries essentially all of the explanatory weight for why the observed answer, so far, still appears to be zero. In 1998, the economist and physicist Robin Hanson published an idea usually called the Great Filter. Whatever process is actually responsible for the galaxy's silence, whatever step between the basic conditions for life and the emergence of a visibly detectable civilization, turns out to be so improbable that it leaves the galaxy empty despite being more than old enough to be full. That step is the filter. The real question is not whether such a filter exists. The silence itself all but requires one to exist somewhere along the line. The real question is where that filter sits relative to where we currently stand. If the filter lies behind us, somewhere in our evolutionary past, then the genuinely hard step might be something like the original emergence of life itself, or the development of complex cells, or the evolution of intelligence. And we would simply be among the rare cases that happen to make it through. If the filter instead lies ahead of us, then most life that reaches roughly our current stage of development does not go on to survive whatever comes next. And we would not be a rare success story so much as a fairly typical civilization approaching a fairly typical ending. What makes Webb's contribution to this question particularly pointed is that every additional planet it confirms as potentially habitable increases the theoretical number of civilizations that should, statistically, have already reached our current stage of development. The more habitable the universe appears to be, the more puzzling and, in a certain sense, unsettling the silence becomes, and the more tightly the great filter, whatever it turns out to be, must be concentrated somewhere in the parts of the story that no telescope has yet been able to observe. It is worth stepping back at this point and looking at how the standard model of cosmology, Lambda-CDM, was actually assembled in the first place. Because understanding how carefully and gradually that foundation was built helps make sense of what it means when cracks begin to show in it now. Lambda-CDM was never constructed all at once, by a single team working from a single unified theory. It accumulated gradually, layer by layer, across many decades of independent observation. Each layer added to explain something the previous version of the picture could not account for. The basic Big Bang framework came first, supported by Edwin Hubble's 1924 discovery that distant galaxies are moving away from us, and later reinforced by the accidental detection of the cosmic microwave background in 1965 by Arno Penzias and Robert Wilson, two researchers at Bell Labs who were actually trying to troubleshoot an unexplained source of noise in a microwave antenna. They checked the equipment for malfunctions. They even removed a nest of pigeons that had taken up residence inside the antenna and cleaned everything thoroughly. The faint background noise persisted regardless, a few miles away at Princeton. A separate team, led by Robert Dick, had independently predicted that if the early universe really had been hot and dense, as the Big Bang model suggested, it should have cooled by now into exactly this kind of faint, uniform microwave signal. When Penzias and Wilson published their puzzling result, both groups quickly realized what had actually been found. The first direct observational evidence that the early universe genuinely had been a hot, dense state that expanded and cooled over time. Exactly as the Big Bang model predicted, dark matter entered the picture through a different line of observation. In 1933, the astronomer Fritz Zwicky studied a cluster of galaxies and noticed that the individual galaxies within it were moving far too quickly for the cluster's visible mass to hold them together gravitationally. Something invisible had to be providing additional gravitational pull. This idea was reinforced decades later, in the 1970s, by the work of Vera Rubin and Kent Ford, who carefully measured how fast stars orbit at different distances from the centers of spiral galaxies, instead of slowing down at greater distances. As expected, if all the mass were concentrated visibly near the center, the stars kept orbiting at roughly the same speed far out into each galaxy's outskirts, implying the presence of a large amount of unseen mass extending well beyond what could actually be seen. Dark energy arrived last, driven by the 1998 discovery, made independently by two teams led by Saul Perlmutter, Brian Schmidt, and Adam Rees, that the expansion of the universe is not gradually slowing down under the pull of gravity, as everyone had assumed it should, but is instead speeding up, as though some additional form of energy were actively pushing space apart. Each piece of this framework was added specifically to accommodate observations that the previous version of the model could not explain on its own. Dark matter accounted for galaxy rotation curves, but was introduced without any accompanying particle physics theory describing what it actually is made of. Dark energy accounted for the accelerating expansion, but remained described only by a placeholder mathematical constant, with no underlying mechanism attached to it. At its core, Lambda-CDM is a framework that performs extraordinarily well when tested against observation, while remaining almost entirely silent about what its two largest components, together making up around 95% of the universe's total content, actually consist of at a fundamental level. This gap in understanding was, for a long time, entirely tolerable, simply because the framework kept correctly predicting new observations as they came in. For roughly 3 decades, it did exactly that. Every new survey, every new instrument, every new measurement came back confirming the model's predictions to ever higher precision. Confidence in the framework grew accordingly. By the time Webb launched, Lambda-CDM had reached a level of confirmed status roughly comparable to where Newtonian mechanics stood at the very end of the 19th century. A framework so thoroughly and repeatedly confirmed across so many independent lines of evidence, that even raising the question of whether it might be fundamentally incomplete had started to feel almost impolite. Within parts of the field, it is worth widening the view a little further, because the four major anomalies already described are not the only small tensions sitting inside modern cosmology. They are simply the largest and most publicly discussed. There are quieter ones too, and the way they cluster together tells its own story. The galaxy two-point correlation function is a technical way of describing how galaxies tend to cluster together at different distances from one another. At the very largest scales, the standard model predicts a specific pattern to this clustering. Several independent surveys have found that the actual observed clustering differs subtly from that prediction, in ways that are each, individually, small enough to sit within the expected margin of uncertainty, but collectively consistent with something the model is not fully capturing. A related measurement, sometimes called the matter power spectrum, describes how matter density fluctuations are distributed across different length scales, and shows a persistent tension between values derived from the cosmic microwave background and values measured directly from galaxy surveys. This particular discrepancy, often referred to using a parameter called sigma 8, which describes the amplitude of matter fluctuations, has shown up repeatedly across multiple independent surveys and multiple different analysis methods. It is smaller than the Hubble tension, and it has been argued about, modeled, and re-examined many times, but it has never been resolved in the direction of simply confirming the standard model. Instead, these smaller tensions accumulate as a broader pattern, one in which the standard model consistently seems to predict slightly too much smoothness and coherence in the early universe, and slightly to little variation in the structure of the late universe. Several other surveys, including the Kilo Degree Survey, the Dark Energy Survey, and the South Pole Telescope, have each contributed measurements sitting in mild tension with Lambda-CDM's predictions. More recent results from the Atacama Cosmology Telescope have tightened these measurements even further. In each individual case, the tension falls below the 5 sigma threshold that would, on its own, constitute a definitive, undeniable anomaly. But in combination, these results begin to sketch the outline of a framework that fits very precisely to the specific era of data it was originally calibrated against, and then starts to strain a little whenever it is tested against independent data, drawn from different cosmic epochs or different physical scales. This is a pattern physicists recognize well from other contexts. A theory fitted carefully to one particular class of observations often performs beautifully within that class, and only begins to show small residual discrepancies once it is pushed outside the range it was originally built and tested for. Those residuals are not, by themselves, proof that the theory has failed, but they are often the earliest signal that a theory's true range of validity might be narrower than everyone had assumed. Lambda-CDM was calibrated primarily against the cosmic microwave background, against the large-scale structure of the relatively nearby universe, and against the expansion history traced by Type 1a supernova. Webb, by contrast, is probing much higher redshifts, corresponding to much earlier points in cosmic history, a regime where the model was always being extrapolated rather than directly tested, and where that extrapolation now appears to be straining under the weight of new data. There is another long-standing puzzle worth mentioning here, sometimes called the lithium problem. Big Bang nucleosynthesis, the process by which hydrogen, helium, and small amounts of lithium were forged during the first few minutes of cosmic history, is generally considered one of Lambda-CDM's greatest successes. The predicted relative abundances of helium and a related element called deuterium agree with what is actually observed to within just a few percent, an impressively tight match. But the predicted primordial abundance of a particular lithium isotope, lithium-7, comes out roughly 3 times higher than what is actually observed in the oldest, most chemically pristine stars that astronomers can study. This discrepancy has been known for decades, and it has resisted every proposed explanation within the standard framework, including uncertainties in nuclear physics, calculations, and various proposed mechanisms by which stars might gradually deplete their own lithium over time. None of these explanations has provided a clean resolution. The lithium problem, taken entirely on its own, is far too small to threaten the overall framework by itself. But it sits alongside the Hubble tension, the early galaxy problem, the DESI dark energy result, and the Great Wall as one more member of a growing family of small, persistent discrepancies that the standard framework was never really designed to accommodate. All at once, it is worth pausing to consider what nucleosynthesis itself reveals about the earliest moments of the universe. During the first roughly 3 minutes after the Big Bang, the universe was hot and dense enough for nuclear reactions to proceed rapidly. Protons and neutrons combined into light atomic nuclei at rates set precisely by the temperature, the density, and the underlying fundamental constants of nature at that time. The resulting mixture, roughly 75% hydrogen and 25% helium by mass, along with trace amounts of deuterium and lithium, depends very sensitively on the exact values of those constants. If the strength of gravity had been even slightly different, the expansion rate during this early period would have changed, altering the temperature at which these nuclear reactions effectively froze and shutting off, which would in turn have produced a noticeably different mix of elements. If the strength of the nuclear force had been even slightly different, the binding energies holding nuclei together would have changed, altering which reactions were energetically favorable to occur at all. The remarkably close agreement between the predicted and observed abundances of these light elements stands as one of the strongest available pieces of evidence that the constants we measure today locally also held those same values during the very first minutes of cosmic history. If it should turn out that the fundamental constants can genuinely drift or evolve over cosmic time, as the DESI dark energy results hint might be possible, an interesting new question opens up: whether they have drifted enough over the entire age of the universe to have any measurable effect on the outcome of those first few minutes. There is an active community of physicists who specifically study possible variation in fundamental constants over cosmic time, testing, for instance, whether certain basic physical ratios have changed since the early universe by carefully examining atomic absorption patterns in the light of extremely distant quasars. So far, results remain broadly consistent with no detectable variation, at least within the precision current instruments can achieve, though that precision remains limited and covers only a fraction of the universe's full history. Given all of this accumulating evidence from several genuinely independent directions, it is worth asking what future observations might do to either resolve or deepen these puzzles. And it turns out there are several major new lines of evidence currently being developed that go beyond anything Webb alone can offer. One promising avenue involves gravitational waves. The LIGO and Virgo detectors have already measured the Hubble constant using an entirely independent technique, observing gravitational waves produced by colliding neutron stars, sometimes called standard sirens. a method that does not depend at all on either the cosmic distance ladder or the cosmic microwave background. Current measurements using this method fall somewhere between the two competing values already in tension with each other, consistent with both, but not yet precise enough to definitively resolve the disagreement. As more of these merger events are detected and the measurements continue improving, the gravitational wave-based expansion rate should eventually either align clearly with one side of the existing tension or settle somewhere genuinely in between, suggesting that both conventional methods have been slightly off in different directions. Next-generation gravitational wave observatories currently in the planning stages, including facilities sometimes referred to as the Einstein Telescope and Cosmic Explorer, would be sensitive enough to detect these kinds of mergers across truly cosmological distances, gathering enough statistics to make this gravitational wave measurement genuinely competitive with the conventional methods already in use. A separate and quite different line of evidence has recently emerged from pulsar timing arrays. These involve carefully monitoring networks of millisecond pulsars, rapidly spinning neutron stars that emit radio pulses with extraordinary clock-like regularity. Because passing gravitational waves subtly stretch and compress space itself, they introduce tiny, detectable timing variations in the arrival of these pulses, effectively turning the entire galaxy into a single enormous gravitational wave detector. Several pulsar timing array collaborations reported evidence around 2023 for a background of gravitational waves at extremely low frequencies, consistent with what would be produced by a large population of enormous black hole pairs, slowly spiraling toward each other throughout the observable universe. This is itself a meaningful cosmological result in its own right, since these giant black hole pairs form whenever galaxies merge together, something that has happened repeatedly throughout cosmic history. The overall strength and shape of this gravitational wave background depends directly on the detailed merger history of galaxies and on the properties of the black holes involved. And comparing the observed background to theoretical predictions places new constraints on models of galaxy formation and black hole growth. Early results suggest the strength of this background may be somewhat higher than the most common theoretical models predicted, which fits neatly into the broader pattern already described, of the early universe appearing to contain more structure, and more of it forming earlier than the standard picture anticipated. Taken all together, this convergence of independent measurements, from gravitational waves, from pulsar timing, from the cosmic microwave background, from galaxy surveys, and from Webb's direct imaging of the early universe, is what makes the current moment in cosmology feel genuinely distinctive, rather than simply another passing anomaly. This is not a single unusual result from a single instrument that might reasonably reflect one systematic error. It is a convergence of independent lines of evidence, gathered by independent instruments, relying on independent physical principles, all arriving at roughly the same region of disagreement with the standard model. Producing that kind of convergence purely by accident would require every one of these separate instruments to happen to share its own independent systematic error, all biased in the same general direction, all of roughly the same magnitude, all pointing toward the same underlying parameters, and all somehow slipping past the extensive cross-checks that every serious research collaboration routinely applies to its own data. The likelihood of that specific combination of coincidences drops rapidly as the number of genuinely independent measurements increases. This is part of why the tone of the scientific conversation around these anomalies has gradually shifted. Over roughly the past 5 years, from cautious skepticism about any single result to something closer to a quiet, somewhat resigned acknowledgement that something real appears to be happening. The language used in published papers has shifted accordingly. The Hubble tension is no longer typically described as a probable systematic effect awaiting a better measurement. It is now more often described as a genuine tension that requires an actual theoretical explanation. The early galaxy problem is no longer usually framed as a likely case of mistaken photometric identification. It is described as a confirmed observational result that the standard model, as currently constructed, cannot fully accommodate. It is worth spending a moment on Webb's own calibration history. Since the history of astronomy includes real cases where an exciting result eventually turned out to be an instrumental artifact rather than a genuine discovery. The Hubble Space Telescope, when it first launched back in 1990, suffered from a flaw in its primary mirror caused by an error introduced during ground testing. A problem later corrected during a servicing mission in 1993 that restored the telescope to its intended performance. The various cosmic microwave background missions, from COBE through WMAP and eventually to Planck, went through repeated generations of refinement, each one tightening the precision of the measurement and, each time, confirming essentially the same underlying picture rather than overturning it. Webb was designed and built with this entire history of hard-earned lessons in mind. Its calibration protocols drew directly on decades of experience from every previous major instrument, and its post-launch verification process was unusually thorough. The broader community's current confidence in Webb's early galaxy results is not simple, uncritical enthusiasm. It reflects a genuinely earned form of skepticism, one that went looking carefully for a mistake and, after extensive checking, did not find one. Looking ahead, there are several major observational projects currently underway or in development that should help clarify, over the coming years, whether these anomalies deepen, resolve, or shift into some new and unexpected shape entirely. Webb itself is expected to keep operating until at least the early 2040s, since its launch trajectory was precise enough to conserve significantly more fuel than originally required, extending the return on what was roughly a $10 billion investment. Each additional year of operation brings new data on early galaxy formation, on the atmospheric chemistry of distant exoplanets, and on the large-scale structure of the cosmic web. The Dark Energy Spectroscopic Instrument will continue expanding its galaxy census, refining the measurement of how dark energy behaves across cosmic time, and either reinforcing or constraining the apparent drift it has already reported. Several new instruments are being built specifically to test these questions further. The Vera Rubin Observatory's Legacy Survey of Space and Time, along with the European Space Agency's Euclid Space Telescope, and eventually a planned square-kilometer array of radio telescopes, will together map the large-scale structure of the universe with far greater breadth and precision than has been achieved so far. These surveys should measure the same baryon acoustic oscillation scale that DESI used, across an even wider span of cosmic history, testing whether the evolving dark energy behavior DESI reported continues in the same direction, changes course, or turns out to have been a temporary statistical fluctuation after all. They will also measure something called the growth rate of structure, essentially how quickly matter clumps together under gravity over time. A quantity that is particularly useful because different theoretical models including various dark energy models and various modified gravity theories, often make distinctly different predictions for it, even when they agree closely on the overall expansion history. Measuring both the expansion history and the growth rate independently, with enough precision, should eventually help distinguish between models that currently fit one but not the other. A distinction the present generation of data is not yet precise enough to make cleanly. On the theoretical side, work is proceeding in parallel. Loop quantum cosmology researchers are developing tools aimed at making precise, testable predictions that can eventually be compared directly against the detailed pattern of the cosmic microwave background. Researchers working on causal set theory are building the computational tools needed to model large-scale cosmic structure, starting from a fundamentally discrete version of space-time. These are slow, careful, painstaking research programs, quite different in character from simply patching small adjustments onto the existing framework, because they represent genuine attempts to replace the underlying substrate of the theory rather than merely extending it. Meanwhile, research building on the holographic principle and JWST continues to reshape how physicists think about the basic nature of space, time, and information, and the eventual resolution of the black hole information paradox. Achieved gradually through decades of work connecting holography to quantum mechanics, stands as a clear demonstration that even very deep, apparently intractable structural puzzles can eventually be resolved once the right conceptual framework is finally found. A number of physicists working specifically on emergent gravity and emergent spacetime believe a similar pattern may eventually apply at the much larger cosmological scale as well, though this remains, for now, an open and actively pursued question rather than a settled result. Improved cosmic microwave background experiments are also on the way. The Simons Observatory, currently under construction, and a proposed successor, sometimes referred to as CMBS-4, would both offer meaningfully better sensitivity than Planck achieved, along with improved methods for separating genuine cosmic signal from foreground contamination originating within our own galaxy. Whether these instruments end up confirming a genuine bubble collision signature within the cold spot, or instead rule that interpretation out entirely, either outcome would be scientifically valuable. Confirmation would represent the first genuine observational evidence for the multiverse concept. A clear exclusion would meaningfully tighten the constraints on inflationary models and on how frequently bubble nucleation events might occur. What none of these ongoing projects can yet tell us is which of these several theoretical directions will eventually produce a successor to Lambda-CDM, capable of resolving all four of the current major anomalies together in one coherent picture. No existing approach currently manages that. Every attempt to modify gravity succeeds in some areas and struggles in others. Every attempt to add new ingredients to Lambda-CDM tends to redistribute the underlying tension rather than genuinely eliminate it. Every attempt at a more fundamental replacement remains incomplete. At least at the level of observational precision the current data now demands. What is happening in cosmology right now is, in its own quiet way, genuinely unusual within the broader history of science. This is not a situation where a revolution has already occurred and the field is simply working out the details afterward. It is also not a situation where nothing unusual is happening at all. It sits somewhere in between. A period where there is enough accumulated understanding to see the general shape of the problem quite clearly, without yet having enough understanding to see the shape of whatever answer eventually resolves it. The anomalies continue accumulating in something close to real time. the careful, hedged language showing up in published papers. Difficult to reconcile, currently unexplained. Challenging existing assumptions is simply how physics tends to sound. Whenever the available evidence is quietly pointing toward something the prevailing model insists should not be possible. There is a recognizable structure buried in the broader history of these kinds of discoveries that is worth naming plainly, because it may say something useful about where things currently stand. Each time physics has been forced to accept that our own particular vantage point is somehow less central, less typical, or less representative than previously assumed, the result has consistently been an expansion of what could ultimately be understood, rather than a diminishment of it. Nicolaus Copernicus, showing that the Earth orbits the Sun rather than sitting at the center of everything, eventually led to Newtonian mechanics and the first coherent mathematical description of the cosmos as a unified physical system. Edwin Hubble, showing that our own galaxy is just one among roughly 2 trillion others, eventually led toward the modern picture of an expanding universe and the entire architecture of contemporary cosmology. The cosmological principle itself, the assumption that we occupy no special or privileged location within a broadly uniform universe, eventually led toward Lambda-CDM and roughly 3 decades of precision. Cosmology, whatever comes next, may represent a 4th step along this same general pattern, one suggesting that even the physical laws and constants we have measured so carefully might turn out to be local rather than truly universal, characteristic of our own particular region of a much larger structure, rather than a complete and final description of everything that exists. This is, for now, simply where the accumulated evidence has led. It does not mean the universe is somehow broken or alien or fundamentally beyond comprehension. It more likely means that the description built up so carefully over the past century was always, in a quiet and understandable way, a local description, one that was extended outward, a little further than the available evidence at the time could fully justify. What scientists genuinely do not yet know is which of the various directions currently being explored will eventually converge into a single successful picture, and how long that process is likely to take. Mercury's perihelion precession waited about 50 years before finding its proper home within general relativity. The ultraviolet catastrophe, by contrast, was resolved within roughly 5 years once Max Planck introduced the idea that energy comes in discrete packets. The question of what actually powers the sun sat unresolved for decades before the relevant nuclear physics was finally worked out. There is no obvious, uniform pattern to how long these transitions tend to take, and nothing here obviously predicts how long the current set of anomalies will remain unresolved. What Webb is doing in the meantime is simply continuing to build the empirical picture with steadily increasing precision. Every additional early galaxy observed at an unexpected mass or an unexpected age tightens the existing constraints on the standard cosmic timeline a little further. Every additional atmospheric measurement of a distant exoplanet adds another data point to the growing statistical picture against which future claims about potential biosignatures will eventually be judged. Every new measurement of large-scale cosmic structure refines our understanding of the initial conditions the universe began with. The telescope is, in effect, functioning as a discovery engine operating right at the boundary, where the existing theoretical framework runs out of confident predictions, doing exactly what a scientific instrument is meant to do, probing the specific regimes where a theory makes clear predictions, and quietly checking whether those predictions actually hold up. The researchers analyzing this data are not pursuing some deliberate campaign to overturn Lambda-CDM out of philosophical dissatisfaction with it. They are simply following the evidence wherever it leads, because that has always been the only genuinely scientific option available. When data produces something unexpected, the appropriate response is to verify it using every available method, to search carefully for alternative explanations within the existing framework. And only once those alternatives have been thoroughly exhausted, to begin the slower, harder work of building a new framework capable of accommodating what the data actually shows. That harder work does appear to be underway now. The anomalies have been checked and rechecked. The most obvious alternative explanations within Lambda-CDM have been carefully explored and, so far, found insufficient. The transition from simply verifying that a problem exists to actually constructing its eventual solution seems to be getting underway, even if the shape of that solution remains genuinely unclear for now. It will likely take real time. It will probably require theoretical breakthroughs that have not yet happened. It may well require entirely new kinds of observational instruments, capable of probing even earlier moments of cosmic history, and even finer details of large-scale cosmic structure than anything currently available. But the general direction of the evidence is reasonably clear. The data appears to be pointing somewhere beyond the edges of the existing framework. Some of the field's most careful and experienced researchers are saying so openly, and the telescope that first revealed the scale of the problem is still up there, quietly gathering more data, still sending back images of a universe that continues to look stranger, deeper, and altogether more surprising than the most precise models built over the last century were fully able to anticipate. This is roughly where cosmology stands right now, not at some final dead end, but somewhere near the edge of a transition whose eventual shape is not yet fully visible from where we are standing. The anomalies are real and well documented. The tension running through parts of the existing framework is real too. The underlying question that Mather's 4 blunt words managed to open up in public is, in its own way, a genuinely old one. Phrased in a new context, what kind of thing is the universe actually turning out to be? And what should we do now that the answer we had been working with for the past 30 years appears to be, at best, only part of the full picture? The telescope keeps looking outward, and slightly backward in time, the way it always has. The data keeps quietly arriving, a little at a time, patiently, the way good data usually does. And somewhere in the space between the careful confirmations of the past and the open questions of the present, there is a kind of comfort in simply noticing how far this whole process has already come. From a faint, unexplained hiss in a microwave antenna on a rooftop in New Jersey, to detailed spectra of galaxies whose light left them before almost anything else in the universe had time to form. None of this needs to be resolved tonight, or any time particularly soon. Entire careers, entire generations of careful, patient researchers are devoted to slowly working through exactly these kinds of questions. One measurement, one paper, one small and carefully checked result at a time. There is something quietly reassuring in that pace, in the sheer unhurried patience of it. The universe does not seem to be in any rush to reveal how the rest of the story goes, and there is no real need for us to rush toward it either. For now, it is enough to simply notice that the questions are genuinely interesting, that they are being asked carefully and honestly by people who know exactly how much care this kind of work requires, and that somewhere out past the orbit of the Earth, A telescope built specifically to look back toward the beginning of everything is still quietly doing its job, one faint point of ancient light at a time.